Nuclear fission means the splitting of atomic nuclei. With fusion, it is exactly the other way around. Here, the atomic nuclei amalgamate. So now let us look at what happens when nuclear fission takes place. Here, the atomic nucleus is hit by a single neutron that is flying around. The impact causes the atomic nucleus to split into two new nuclei. Each of them takes part of the electrons with it, so that two new atoms are formed. In the case of some very large atoms, a few neutrons are additionally released. When uranium atoms are split in a nuclear power plant, this usually involves the release of 3 neutrons. These can then affect the next fission processes in a chain reaction. And finally, energy is released, and very much of it at that. 1 kilogram of naturally occurring uranium has the energy of 12,000 liters of mineral oil, or of almost 19,000 kilos of hard coal. As in the case of the nuclear fusion on the Sun, it is in fact 4 hydrogen atoms, that means 4 protons, that amalgamate to form a helium atom. But as the latter only has room for 2 protons in its nucleus, the other 2 are released, similar to the excess neutrons upon the fission of uranium. And of course, this also involves the release of a lot of energy, even more than upon nuclear fission. It would only need 1 single gram of fuel, or the hydrogen isotopes deuterium and tritium, to gain as much energy as from 12,000 kilos of hard coal.
So, what does a light water reactor do? Well, the basic principle is shockingly simple. It heats up water using an artificial chain reaction. Nuclear fission releases several million times more energy than any chemical reaction could. Really heavy elements on the brink of stability, like uranium-235, get bombarded with neutrons. The neutron is absorbed, but the result is unstable. Most of the time, it immediately splits into fast-moving lighter elements, some additional free neutrons, and energy in the form of radiation. The radiation heats the surrounding water, while the neutrons repeat the process with other atoms, releasing more neutrons and radiation in a closely controlled chain reaction. Very different from the fast, destructive runaway reaction in an atomic bomb. In our light water reactor, a moderator is needed to control the neutron's energy. Simple, ordinary water does the job, which is very practical since water's used to drive the turbines anyway. In 1979, the 3 Mile Island nuclear plant in Pennsylvania barely escaped a catastrophe when its core melted. In 1986, the Chernobyl catastrophe directly threatened Central Europe with a radioactive cloud, and in 2011, the drawn-out Fukushima disaster sparked new discussions and concerns. 3 reasons why we should stop using nuclear energy. 1. Nuclear weapons proliferation. Nuclear technology made a violent entrance onto the world stage. Just 1 year after the world's first ever nuclear test explosion in 1944, 2 large cities were destroyed by just 2 single bombs. After that, reactor technology slowly evolved as a means of generating electricity, but it's always been intimately connected with nuclear weapons technology. It's nearly impossible to develop nuclear weapons without access to reactor technology. 1. Nuclear energy saves lives. In 2013, a study conducted by NASA found that nuclear energy has prevented around 1.8 million deaths. Even if you include the death tolls from Chernobyl and Fukushima, nuclear energy ranks last in death per energy unit produced. While nuclear waste is really toxic, it's usually stored somewhere, while the toxic byproducts of fossil fuels are pumped into the air we breathe every day. So, just by reducing the amount of fossil fuels burned, countless cases of cancer or lung disease and accidents in coal mines have been avoided. If we can choose between lots of dangerous stuff being put into a deep hole and lots and lots and lots of dangerous stuff being pumped into the atmosphere, the former seems more logical. 2. Nuclear waste and pollution. Spent nuclear fuel is not only radioactive, but also contains extremely poisonous chemical elements like plutonium. It loses its harmfulness only slowly over several tens of thousands of years. And there is also a process called reprocessing, which means the extraction of plutonium from spent nuclear fuel. It can be used for 2 purposes: to build nuclear weapons or to use it as new fuel. But hardly any of it is used as fuel because we don't have the right kind of reactors for that. A milligram will kill you, a few kilograms make an atomic bomb, and even an inconspicuous country like Germany literally has tons of the stuff just lying around because reprocessing sounded like a good idea decades ago. 2. Nuclear energy reduces CO2 emissions. Nuclear energy is arguably way less harmful to the environment in terms of climate change than fossil fuels, our main source of energy. Since 1976, about 64 gigatons of greenhouse gas emissions have not been pumped out thanks to nuclear energy. 3. Accidents and disasters. Over 60 years of nuclear power usage, there have been 7 major accidents in reactors or facilities dealing with nuclear waste. 3 of those were mostly contained, but 4 of them released significant amounts of radioactivity into the environment. In 1957, 1987 and 2011, large areas of land in Russia, Ukraine and Japan were rendered unfit for human habitation for decades to come. The number of deaths is highly disputed, but probably lies in the thousands.
First, you need to write the nuclear reaction equation for this fission. So what's happening is the uranium nuclide, and I'm going to write it in this format for writing the equations, is bombarded with 1 neutron, which is written like that, and it gives 137 tellurium. Tellurium has 52 protons, and it gives 97 zirconium, which has 40 protons. So what you want to do here is figure out the rest of the products, because that's not all. And what you really want to do here is account for the number of neutrons. So remember this format where you had X representing your chemical symbol, A representing your mass number, which is the number of protons plus neutrons, and Z representing your atomic number, which is the number of protons. So what you need to do to find the number of neutrons is subtract Z from A. So that's what I'm going to do for all of these elements. So the number of neutrons in the uranium-235 is 143, and of course the neutron contains 1 neutron because it is a neutron. And together you have 144 neutrons in the reactants. Tellurium, if you subtract 52 from 137, you get 85 neutrons, and zirconium has 57 neutrons. So in total, you can see so far your products have together 142 neutrons. So you're 2 neutrons short. There are 2 more neutrons in your reactant than in your products. So what you want to do is add 2 neutrons to balance that out. So you're basically balancing the neutrons here. So that is your completely balanced equation for neutron-induced nuclear fission of uranium-235 when it goes to tellurium and zirconium. So now what you want to do is you want to find the mass loss by adding up the mass of the reactants and the mass of the products, and then you want to plug that mass loss into the E equals mc squared equation. So let's first do the mass of the reactants. Uranium-235, we're given the mass is 235.04392 atomic mass units, or AMUs, and then the mass of a neutron is 1.00866 AMUs. Add those 2 together, you get 236.05258 AMUs. And then the mass of your products, you have the mass for tellurium-137 being 136.92532. The mass of zirconium is 96.91095, and then you have 2 neutrons on that side, so it's 1.00866. And you add all of those together, you'll get 235.85359. So to get the mass loss, you want to subtract the mass of the reactants from the mass of the products. And when you do that, what you get for your mass loss is 0.19899 AMU. And notice we've moved from 1, 2, 3, 4, 5, 6, 7, 8 significant figures for that mass of uranium, for example, to now 5 significant figures. So that's what you're going to consider when you do your E equals mc squared calculation. So that's the next step. Before you plug in your mass to the E equals mc squared equation, AMUs has to be in kilograms, and you'll see why that is in a minute. So to convert AMUs to kilograms, you have to know that there are 1.66054 times 10 to the negative 27 kilograms in 1 atomic mass unit. So that's going to give you 3.30431 times 10 to the negative 28th kilograms. So now you plug things in to the E equals mc squared equation. So your mass is 3.30431 times 10 to the negative 28 kilograms, and the speed of light is going to be 2.9979 times 10 to the 8th meters per second, and that term is squared. What you're going to get there is 2.9697 times 10 to the negative 11, and the units are going to be kilogram meters squared per second squared, which is actually equal to a joule. So your answer is 2.9697 times 10 to the negative 11th joules of energy are released.